Welcome to the Deep Dive. Today we're getting into something pretty fundamental for anyone who's ever worked with networked computers accessing files somewhere else, like they're right there on your own machine.
That's right. We're talking about the network file system, NFS. It's basically the magic that lets different machines share files across a network.
Exactly. And for this deep dive, we've looked at, well, quite a bit history. The RFCs detailing the specs, how it evolved across different platforms.
Yeah, a good mix of sources.
So our mission, if you will, is to really get our heads around what NFS is, how it grew up, version by version, and maybe why it's still so important today.
Sounds good. Where should we start? The beginning.
Yeah, let's do that. Where did NFS come from?
Okay, so the story kicks off back in 1984. Sun Microsystems. They needed a way to share files easily in their networks.
Right, Sun was a big player then.
Oh, absolutely. And NFS wasn't built from scratch entirely. It relied on something they already had called the Open Network Computing Remote Procedure Call System, ONC RPC.
Okay, so it had a foundation. Was it a proprietary Sun thing, though? Lockdown?
No, not at all, actually. And that was key. They intended it as an open standard right from the get-go. The IETF, the Internet Engineering Task Force, they formalized it through RFCs, requests for comments.
Ah, RFCs. So anyone could implement it.
Pretty much. That openness was crucial for it catching on everywhere. But interestingly, the very first version, version 1, purely internal at Sun, they never released it outside.
Just testing the waters in-house first. Makes sense. So what happened after V1?
Well, they learned from V1, tweaked things, and when they were ready to go public, that became version 2. It also meant they could think about, how different versions might work together, maybe fall back if needed.
Smart. Planning ahead. So NFS V2, that's where the public story really starts.
That's the one. NFS version 2. It's laid out in RFC 1094 from 1989. And its architecture was, specific. For starters, it mainly used UDP, the User Datagram Protocol.
UDP. Okay, not TCP initially.
Not primarily, no. And a really core design idea was keeping the server stateless.
Stateless? What does that mean in practice? Why do it that way?
Stateless basically means the server doesn't remember anything about the client from one request to the next. Every single request has to contain all the info the server needs. The idea was simplicity on the server side.
Simpler server, okay.
Yeah.
But are there downsides? What about something like file locking?
Exactly. That's the trade-off. Because the server was stateless, handling locking reliably within the core protocol was, tricky. So locking had to be implemented separately.
So it wasn't built in. Could that cause problems?
It was a conscious design choice, yeah. And it led to things like the Network Lock Manager, NLM. That became the common sort of sideband protocol just for handling locks with NFS v2.
Gotcha. So NLM handled the locking part. And who were the key people behind V2?
Oh, definitely need to mention Russell Sandberg, Bob Land, Bill Joy, Steve Kleiman, among others. Their work really set the stage.
Pioneers. Wasn't there something about making it work across different OSs?
Yes, the Virtual File System Interface, VFS. That was super important. It acted like a translation layer, letting different operating systems plug into different file systems, including NFS, made it modular.
So that helped it spread quickly.
Hugely. By early 1986, so just a couple of years in, you could already find NFS v2 running on systems like System V Release 2, MS-DOS, even VAX VMS using this thing called Unis.
Wow, that is fast adoption. Impressive. But I seem to remember hearing about a pretty major limitation with V2. Something about file size.
You do remember correctly. Big one. Because it used 32-bit numbers for file sizes and where you were in a file, the offset, NFS v2 couldn't handle anything bigger than 2 gigabytes.
2 gigs. That sounds tiny now, but even back then, that must have started to pinch.
Oh, yeah. As data grew, 2GB became a real wall, which leads us nicely into
NFS version 3.
Exactly.
What did V3 bring to fix that and, improve things overall?
Right, NFS v3, standardized in RFC 1813-1995. It tackled several v2 issues head-on. The absolute headline feature was support for 64-bit file sizes and offsets.
Ah, okay. So goodbye 2 dB limit.
Gone. Suddenly, NFS could handle much, much larger files. A fundamental fix.
Huge. What else was new in version 3? Performance stuff.
Definitely a focus on performance.
Yeah.
V3 introduced asynchronous writes on the server side.
Asynchronous writes. How's that different from V2?
In V2, writes were usually synchronous. The client would send the data and basically had to wait, twiddling its thumbs, until the server confirmed, yep, written safely to disk.
Ah, okay. Slows things down.
Can do, yeah. Asynchronous writes meant the server could just acknowledge the request much faster, saying, got it, I'll write it, letting the client get on with other things. It generally boosted write performance noticeably.
Makes sense. Better responsiveness. Anything else?
Yeah, a couple of other nice touches. Replies from the server started including more file attributes. Seems small, but it meant the client didn't have to keep asking for the same info again and again. More efficient.
Fewer round trips. Always good.
And there was a new operation, Reeditor Plus. Quite clever. It let the client grab not just the file names in a directory, but also their file handles and attributes all in one go.
Again, fewer network calls. Faster directory listings, I guess.
Pretty much. So what was the main push for V3? Just the file size limit and performance?
That seems to be the main story. Inside Sun, the initial driver was definitely fixing those performance issues, especially the synchronous writes from V2.
Right.
But yeah, as the early 90s went on, that 2 GB limit was becoming a bigger and bigger headache for people. And something else was happening around then, too. TCP was getting more popular, wasn't it?
Ah, yes, TCP/IP was really taking hold. While some folks had already experimented running NFS v2 over TCP, Sun made it official with v3. They added TCP support alongside the v3 release.
And TCP has advantages over UDP for this kind of thing, doesn't it? Especially over wider networks.
Big advantages. TCP is reliable, connection-oriented. That made running NFS over, say, a wide area network, a WAN, much more practical. UDP's connectionless nature meant packets could get lost or arrive out of order, which is way more likely over long distances.
More robust.
And TCP also allowed for bigger chunks of data in reads and writes. You could push past that typical 8 KB limit you often had with UDP. So NFS was starting to stretch its legs beyond the local network.
Okay, interesting. Now, I saw a mention of something called YANFS, or WebNFS. What was that about?
Ah, YANFS, yet another NFS, which they later called WebNFS. It was an extension mainly for V2 and V3. Its big goal was making NFS work better through restrictive firewalls.
Firewalls. Always a challenge.
Yeah.
How did YANFS help? Traditional NFS needed multiple ports.
It often did, yeah.
Yeah.
You had port map, the mount protocol. Could be a real pain to configure firewall rules for all that. YANFS tried to simplify it.
How?
Two main things. First, it pushed for using a single fixed TCP/UDP port, port 2049.
Okay, one port is easier than many.
Much easier. Second, it introduced the concept of a public file handle. Instead of the client having to first talk to the mount service to figure out how to access a file system, it could use the standard, well-known starting point.
Like a default entry point.
Exactly. It was a null handle for V2, zero length for V3. Think of it as just knowing the server's main door, simplifying that initial connection, especially through a firewall.
Makes sense. Streamlining the handshake.
Precisely. And these ideas, the single port and the public file handle, they were so useful they actually got rolled into NFS v4 later on. YANFS also evolved a bit beyond just the firewall stuff, adding some server-side improvements too, sort of a stepping stone.
Right. Which brings us neatly to NFS v4. This sounds like a really big jump.
Oh, massive. Version 4 was a major evolution, initially defined in RFC 3010 back in 2000, and then revised since. It took ideas from other systems too, like AFS, Andrew File System, and even SMB, the Windows File Sharing Protocol.
So learning from others, what were the headline features of v4?
Key things were big performance boosts, mandatory strong security that was new, and a shift to a stateful protocol.
Stateful? But weren't the earlier versions stateless? That sounds like a fundamental change.
It was a huge change. Going stateful meant the server now did keep track of clients and what they were doing. It allowed for much more advanced features, better locking, caching, things called delegations. Yeah, where the server could basically grant a client temporary exclusive control over a file, cutting down on network chatter. But yes, it definitely made the server more complex compared to the old stateless design.
Trade-offs again, more features, more complexity. And v4 was developed differently too, wasn't it?
Crucially, yes. It was the first version developed under the IETF banner. Sun had handed over the reins for future development, so more of a community-driven standard from v4 onwards.
That's significant. And v4 didn't stop there, right? There's v4.1, v4.2.
Correct. NFS v4.1 came along around 2010, RFC 5661, also updated since. Big focus there was supporting clustered servers, multiple servers working together, and the star feature was PNFS.
PNFS, parallel NFS. What's that about?
Okay, PNFS is pretty cool. The core idea is splitting the metadata, the file names, permissions, directory structure, completely away from the actual file data.
Separating structure from content.
Kind of. It allows the client to access file data that might be spread across multiple data servers, all in parallel. Imagine fetching different chunks of a huge video file from several storage nodes simultaneously.
Ah, so potentially much faster access for large files or high-demand situations.
Exactly. Huge for scalability in big data centers and high-performance computing.
Makes sense. And V4.1 had other things too. You mentioned multipathing.
Yeah, session trunking, or NFS multipathing, lets a client use multiple network connections to the same NFS server. Good for resilience if one path fails, and potentially more bandwidth. You see that in things like VMware ESXi.
Okay. And then NFS V4.2, what did that add?
V4.2 arrived in 2016, RFC 7862. Added a whole raft of new features. Server-side clone and copy, really efficient ways to duplicate files or parts of files directly on the server.
Saves pulling data back and forth just to copy it.
Precisely. Also things like application I/O advice, where an application can give hints to the server about how it plans to access data, like, I'm going to read this sequentially.
Helping the server optimize.
Plus support for sparse files, better space reservation, something called application data blocks, ADB, labeled NFS for integrating with security systems like Linux, and new operations specifically for managing PNFS, like layouter and layout stats.
Wow, quite a list. V4 really packed in the features. And you said earlier V4 also simplified the firewall situation.
Yes, that's a major practical win. Unlike the old days, NFS v4 generally just uses that single TCP or UDP port 2049 for everything. Mount, locking, data transfer, all through one port. Much, much easier for firewall admins. Echoes that original YANFS idea.
Definitely a welcome simplification.
Yeah.
So, okay, we've walked through the main versions. What about those other bits and pieces, the sideband protocols and extensions?
Right, the ecosystem around NFS. We touched on WebNFSEA and NFLRD browser integration, firewall ease of use. Sun actually open sourced their client for that in 2007.
Okay.
Then the Network Lock Manager, NLM, crucial for V2, V3 file locking, data integrity when multiple clients are involved. There's RQATAD remote quota reporting, lets you check how much disk space you're using on the server.
Handy for users and admins.
Yep. For really high-speed needs, there's NFS over RDMA, uses remote direct memory access for super low latency transfers, cuts out a lot of the usual network stack overhead.
For HPC, scientific computing, that kind of thing.
Exactly. And NFS Ganesha is interesting. It's an NFS server that runs in user space, not the kernel. It's flexible, can serve data from various backend file systems like GPFS or CephFS using these pluggable modules called FSL.
File system abstraction layer, right.
That's the one. And finally, there was Trusted NFS, TNFS, focusing on tighter security. So yeah, a whole suite of things grew up around the core protocol.
A rich ecosystem. Now, the whole point is sharing across different machines. How widely supported is NFS? What platforms actually run it?
Oh, the list is huge. It really speaks to how successful and, frankly, necessary it was. Pretty much every Unix-like system supports it out of the box. Solaris, AIX, HPUX, FreeBSD, NetBSD, OpenBSD, and, of course, Linux in all its flavors.
The Unix world, definitely. Anywhere else.
Yep. AmigoS, Archaeos, Haiku, IBM i, the old AS400, Mac OS, Microsoft Windows has clients and servers, MS-DOS even had clients back in the day, Novell NetWare, OpenVMS, OS2, RASC-OS, it's pretty much everywhere.
That is seriously widespread. Though on some of those, NFS isn't the native or default way of sharing files, is it?
That's a fair point. While they support NFS, they might have their own preferred protocol. Like IBM i has its own OS400 file server thing. Mac OS traditionally used AFP, Apple Filing Protocol, though it leans more towards SMB now too. Windows, of course, defaults to SMB-CIFS. Novell NetWare had NCP.
Right.
But having NFS available on all these platforms is key for interoperability. It gives you a common language for file sharing when you have a mix of different systems.
The universal translator for files.
Yeah.
Let's maybe zoom out a bit. Think about the history. How did NFS fit into the broader landscape of networking tech back then? Were there competitors?
Oh, definitely. NFS development didn't happen in a vacuum. Apollo Computer, another big workstation vendor back then, had their network computing system, NCS. It did similar remote procedure call stuff to Sun's ONC RPC that NFS used.
Okay, so Sun had ONC RPC, Apollo had NCS. Did they work together?
Not really smoothly. There was a pretty fundamental disagreement about how to represent data on the network, specifically things like integers. Sun's way, XDR, always used big endian byte order. Always.
Regardless of the machine.
Right. Predictable, simple. NCS tried to be clever. It would check if the two machines talking had the same endianness, and if so, it wouldn't bother swapping bytes. Potentially faster, but more complex.
Yeah, the classic standards fight. Strict compatibility versus potential optimization.
You got it. There was even an attempt by a group called the Network Computing Forum to merge the two approaches in '87, but it didn't really work out.
Okay.
And around the same time, things got complicated politically. Sun and AT&T, who had their own competing thing called Remote File System, RF.
RFS.
They announced they were going to work together on UNIX System V Release 4. This made other big Unix vendors nervous, BEC, HP, IBM. They worried Sun and AT&T would dominate.
So they reacted.
They did. They formed the Open Software Foundation, OSF, in 1988, partly as a counterweight.
Wow. Okay. So Sun was pushing NFS, AT&T had RFS, and then OSF came along.
Exactly. And the irony is, before the Sun AT&T deal, vendors like DT, HP, IBM had already started adopting Sun's NFS over AT&T's RFS. NFS just seemed to gain traction faster.
Why do you think that was?
Openness probably helped, and maybe it was just, technically solid and available early. Plus, Sun pushed these things called connectathons starting in '86.
Exathons.
Yeah, basically events where different vendors could bring their NFS implementations and test them against everyone else's. Vendor-neutral testing really helped iron out incompatibility bugs.
Smart. Building interoperability through collaboration.
Yeah.
So what did the OSF do about file sharing? Did they adopt NFS?
Nope. They went a different way. They chose the Distributed Computing Environment, DCE, which included its own Distributed File System, DFS. DFS was based on AFS, the Andrew File System, and it used DCE's own RPC mechanism, not Sun's ONC RPC.
So competing standards again, NFS versus DFSFs. How did that play out?
Well, there were attempts to standardize DCE RPC through the IETF, but OSF wasn't keen on giving up control. The IETF ended up extending Sun's ONC RPC instead, adding better security with RPC-SEC GSS.
Okay.
And later, as we said, Sun agreed to let the IETF take charge of new NFS versions, starting with V4. That agreement specifically excluded V2 and V3, which Sun kept control of, but it paved the way for NFS V4 becoming an official IETF standard in 2003.
A big step towards vendor neutrality for the filter of NFS. So what happened to DFS and AFS in the long run? Did they challenge NFS and maybe SMB?
Commercially. Not really, not on the same scale. By the early 2000s, it was pretty clear that NFS and SMB were the dominant protocols in most enterprise environments. IBM, who had bought Transarc, the main company behind DFS and AFS, they eventually donated a lot of the AFS source code to the open source community around 2000. That became the Open AFS project. And then in 2005, IBM basically stopped selling AFS and DFS altogether.
So NFS and SMB largely won that battle for widespread adoption.
Yeah.
Okay, let's circle back to the more recent stuff. You mentioned PNFS and V4.1 proposed by PANASYS. What was the core idea there again?
Right. PANASYS was big in parallel storage. Their PNFS proposal for NFS v4.1 was all about boosting data access speed through parallelism. The key insight was separating the file metadata, the directory structure, file attributes from the actual file data location.
Okay, separate metadata server, data server.
Essentially, yes. And crucially, PNFS allows the file data itself to be striped across multiple data servers. So unlike traditional NFS, where one server usually handles everything for a file, with PNFS, the client talks to a metadata server to find out where the data pieces are, and then it can talk directly and often in parallel to the different data servers holding those pieces.
So the client gets told chunk 1 is on server A, chunk 2 on server B, and goes straight to them.
Exactly. It bypasses the potential bottleneck of funneling all data through a single NFS server. Much more scalable, much faster for parallel workloads.
That sounds like a really significant architectural shift for high-performance needs.
Yeah.
And you said V4.1 brought other things besides PNFS.
Quick recap, sessions for more robust connections, directory delegation and notifications for better client caching, multi-server namespace to build a single view across several servers, ACLs for finer-grained permissions, retention attributions, SES and phone name for security. Quite a bit packed into 4.1.
It's really clear NFS hasn't stood still. It's evolved dramatically from that initial Sun design.
Absolutely. It's had to adapt, from its beginning solving Sun's internal needs through the 2 GB limit, adding TCP, tackling firewalls, embracing statefulness and strong security in V4, and then pushing into parallel access with PNFS. It's kept changing to meet new demands.
It really shows its resilience and the value of that open approach, allowing it to be adopted and adapted so widely across so many different systems and networks.
Definitely. It's provided this consistent, reliable way to share files for decades now.
So wrapping this up, what does this journey mean for you, our listener? Well, whether you're deep in network administration or just curious about how computers talk to each other, understanding NFS gives you a real appreciation for a technology that quietly makes so much of modern computing possible.
And that brings us to a final thought, a question for you to maybe chew on. With cloud storage becoming so pervasive, Dropbox, Google Drive, S3, and all these other ways we share files now, What's the future for a protocol like NFS? Does it still have a major role to play? Where does it fit in this evolving landscape?
That's a great question, something to think about. Where does this venerable yet still evolving protocol fit next?